Welcome to the final version of our machine learning seminar. Today, we're really pleased to have Joe Hogan, who is the chair of Biostatistics at Brown. Joe is an expert in causal inference and missing data, has written books on this, and we're really happy to have him today to talk about the role of machine learning in predictive and causal inference. Joe's work, his research concerns the development and application of statistical methods for large-scale observational missing data. He's interested in causal inference, missing data, and quantifying uncertainty associated with untestable assumptions. Nearly all of his work is motivated by applications in HIV and AIDS and in infectious disease. For the past several years, he's co-led an NIH-funded international training program designed to build research capacity in biostatistics at Moi University in Kenya. So Joe, I'm going to turn it over to you, and thanks again for leading this. And if you have questions, please put them in the chat. We'll leave it up to Joe to how he wants to handle those, but I'm happy to relay them to him as we go. And we'll have time at the end for question and answer.
Okay, thanks, Chris. And thanks to the group for the invitation, and thanks for attending late in the afternoon on a stormy day. So I guess there's definitely notation in this talk, and I'll just try to walk through it carefully. But I thought that instead of going into like really technical issues related to what is machine learning and getting under the hood and that kind of thing, I think I would just I'll present it as kind of a tool that I use to do sort of to answer bigger picture questions. So first, I thought it would be useful to distinguish between predictive and causal inference. It's confusion I see sometimes, even now when I read the literature. And so predictive inference is concerned with predicting some outcome Y from a set of inputs X. So here's some examples I've put here in the bullet points. Maybe predicting a failure to show up at an next clinical appointment, predict 5-year mortality, predict presence of fetal heart defect using image data. That could be a really complicated example. Typically, we're just, we have some inputs and we want to generate a prediction of either what's happening under the hood or what might be likely to happen in the future. So predictive rules are usually built using statistical machine learning. So that's where I think machine learning can be a tool in service of a larger goal. So this is some notation, and essentially, again, I'll walk you through it. So this is a probability. One of the probability associated with some event happening, conditional on some set of inputs X. So usually we just use like some kind of a function. If we fit a logistic regression, it could be an inverse logit function. But the function G is sort of generic. And you've probably seen in the presentations that have happened up to now, machine learning or the prediction function could be a regression function. It could be random forest, classification tree. There's lots of, multi-layer neural networks, deep learning algorithms, etc. So G is just like something I apply to the predictors to get a prediction of an outcome. So generally, to generate predictive inferences, we like to see temporal ordering. We like the predictors to come before the outcome. We'd like to see lots of replicates of the predictors and the outcome observed in pairs from some representative population. And then we need some tools, some analytic tools. Essentially, those tools comprise methods to train and validate statistical models or statistical algorithms. And what I mean by that is that, what we try to do is what we try and do is just see if the sort of the fitted model agrees with the observed data. So now we think about like predictive versus causal inference. Sorry, I'm clicking on the wrong thing. I apologize. I'm trying to get a window to disappear, but okay. So if we think about predictive versus causal inference, this is where maybe some of the confusion comes up, but also maybe where some of the confusion can be cut through. These two statements, one of which is a predictive inference or predictive statement, and one of which is a causal statement, can both be simultaneously true. So it could be true that, for example, if we're thinking about HIV treatment, those who receive HIV treatment immediately upon diagnosis have a shorter survival time on average than those who wait. That could be true if we're looking, for example, at an electronic health record or some observational data. It can also be true that given the choice to treat immediately or wait until symptoms develop, treating immediately will lead to longer survival on average. So what I'm saying is that it could be true that giving that in an observational data set, where we just sort of collect some data and look at associations, or even look at correct predictive associations. If we wanted to predict who's going to survive longer, we might say, well, those who got treatment sort of later after their diagnosis actually in this data set survive longer. It could also be true that giving some of the treatment earlier is better for them if the choice is made at the time of diagnosis. So, and the reason that could be true, for example, in an observational data set, there's a phenomenon that physicians are only treating patients who are sicker when they, in other words, are treating sicker patients earlier. Then getting treated early is in a sense a marker for being more advanced in the disease stage. So that's why earlier treatment would be prognostic of shorter survival. So this brings us back to the question, if we're concerned with causal inference, and often we are, a lot of times a goal of using electronic health records is to ascertain, what's better, what kind of treatment is better, what kind of intervention works better. We're sort of restricted to observational data. What do we need to make causal inference? So first, we need some sort of plausible model of a causal effect. That is like a model that tells us if we administer treatment, something physiologic is going to happen, at least a hypothesized mechanism. So for example, if we give someone antiviral therapy, the mechanism our plausible mechanism is that the antiviral therapy will slow down viral replication, and that will lead to sort of reconstituted immune function. If we have that plus some randomized exposure randomized assignment rather to the exposure of interest, if we had those two things in combination, we actually have the tools to draw causal inference. And that's why, randomized trials are sort of the gold standard for understanding what kind of therapies or interventions work, because if we sort of allocate treatment randomly and we sort of can time order we have control over the time ordering of the exposure and the outcome, we have the two major ingredients needed to draw causal inference. But with observational data, most of the time, we don't have the second piece. We don't have sort of a random allocation of treatment. And so the methods that have been designed to draw causal inferences or, more generally control for confounding or imbalance between exposed and unexposed or treated and untreated groups, all are designed to mimic this notion of randomly allocating the exposure. So whether it's matching, which is kind of intuitive, or we just find people who are similar on their characteristics, one of which is exposed and one of which is not. That's one way to sort of mimic randomization. There's inverse probability weighting, where we sort of construct a pseudo sample where individuals are weighted up or down relative to their probability of receiving treatment in an observational setting. There's covariate adjustments such as regression, and then sort of standardization, which is an old epidemiologic technique for comparing populations or comparing exposed and unexposed populations. All right, so let me just, okay. So AMPATH is a program that I work with. It's a large scale HIV care program in Kenya. This program takes care of about 250,000 people with HIV, and at any given time, about 150 to 200,000 individuals are enrolled in care. And because of the sort of large scale, and because of the sort of the number of questions that come up as far as like what's the best way to treat people with HIV, not only for their HIV, but also for comorbidities, what's the best way to monitor treatment, a lot of interesting statistical causal questions come up. And this particular collaboration motivates a lot of my work lately. So the work I'm doing lately really is like, how to use a large observational data set, a large complicated data set to draw both causal inferences and predictive inferences, not necessarily at the same time, but those two questions come up a lot. or those two types of questions come up a lot. So what what I'm going to use to frame a couple of the questions, a couple of statistical analyses I'm going to show you is something called the HIV care cascade. And the term care cascade comes up in a number of different contexts, a disease-specific kind of context, where there's sort of a progression through treatment and recovery that enables us to understand like what's the best way to handle like either acute or chronic diseases. So the HIV care cascade is a conceptual model, and it sort of describes the progression of stages through HIV care, starting with the identification of new cases, the linkage of those new cases to an appropriate care program, then initiation of treatment. And once treatment is initiated, retaining people in care, and then ideally getting them to have good clinical outcomes. So this is like an animating concept that's used not only to dictate like research and care agendas, but also like to frame policy goals. And so when we're conducting research on the delivery of care or healthcare outcomes, often we'll frame these analyses in the context of the HIV care cascade. So here's just a cartoon version. And what you see here, these are just some of the stages that I described before. The HIV care cascade, or in this case, is called the continuum. If you look at it, it's sort of a temporal ordering of events. And in a sense, a person can be in one of these states at any given time. So, you know, the first one being diagnosed with HIV is sort of being diagnosed prior to being linked to a care program. And then we have the successive stages. So the transition between these stages are seen as essential to understanding sort of, you know, what sort of, so the causal question that we like to understand is like, what sort of factors and what sort of policies promote progression from one stage to another? So what sort of policies promote engagement in care? And then the other thing we often like to do is like predict events. We want to predict, say, either good outcomes or bad outcomes. So in the context of caring for patients, we accumulate data, and we might want to know in advance, like, can we predict which patients are going to not achieve viral suppression and then maybe intervene? But we also want to ask causal questions like, well, if we intervene by sending someone out to the house a week before the visit, is that going to make somebody more likely to be, say, retained in care than if we do the usual and just send like a text message? So that's like a causal question. So both causal and predictive questions are framed often in terms of the outcomes or in the transitions associated with this HIV care continuum. So I guess I mentioned a few of these. So they're both, you know, predictive questions that come up in research about HIV care, and also causal questions that come up. All right, so maybe I can stop here and just see if there are any specific questions I can answer about the difference between like goals for predictive inference and goals for causal inference. And I you know, I would welcome questions along the way too, but I can stop to see if there are any up to now. All right, nothing yet.
No, I don't see any. So
okay. All right, that's fine. All right, so some researchers have tried to formulate like models of the entire cascade. And you can see here, this is a paper by one of my colleagues, Michael Mugavero. He and his colleagues sort of conceptualized the cascade, and then there have been, you know, attempts to sort of model the entire cascade as what we call in statistics a state transition model, looking at the the probabilities of moving from one stage to the next. And what you can see here is that people can sort of move backward and forward through stages. They can drop out of care. They can drop back in. It's sort of not as straightforward necessarily as the cartoon version I showed you a couple of slides ago. So to focus this discussion a little bit, we're going to look at modeling state transitions over time in terms of, and focus on the part about engagement in care. So what you see here is a representation of one part of the cascade. We've sort of broken it down into pieces. And each of these arrows represents one-step transition from like one visit to the next for an individual patient. So for example, if you can see this pointer, let's suppose at a particular point in time, a person is engaged in care. So the arrow represents what their state would be at their next scheduled visit. So if they don't show up, they would be disengaged. So they would have made the transition from engagement to disengagement. If they missed a visit, but then at their next scheduled visit after that, they came back, then they would have made the transition from disengagement to engagement. If a person shows up for 2 consecutive visits, this sort of circular arrow just says that at the next step, they went from engaged to engaged. Now, there's a couple of other states you can go to. People can transfer out of care because they move, they transfer out of the care at that location, or obviously there's mortality. So there's lots of different transitions. You can see, even if you're just talking about the engagement and care process, there's multiple sort of states to consider. So with machine learning, we're often dealing with complex data sets, and this is an example of data from one individual. And what we see here is the time axis goes from 0 to 3,000 days, and 0 is time of enrollment. And each vertical line is an encounter with the care program. It could just be picking up your drugs, but it could be a scheduled clinical visit. If the line is dashed, that means you're not taking therapy. If the line is solid, it means you are taking therapy at the time of that visit. So just with these, gray lines dashed and solid, we've picked up a couple of processes here: the visit schedule, so the visit process and the on-treatment process. Overlaid on top of that are a number of time-varying clinical variables. Here I've just modeled, or I've displayed CD4 count. At the beginning, CD4 count was low. A person went on treatment, you see their CD4 count went up. That's a measure of immune function. So the higher it goes, the better. Seems to have started to falter here. Possibly the person was in a phase where they switched treatments and then made a bit of a recovery. So that's sort of a progression of some of the data. And then the intervals are colored with color codes. Green means you're engaged. Red and shades of red mean you're disengaged. So this sort of peach color here means that, well, you were disengaged during this period of time. And then when the peach color gets darker and darker, that means like you're sort of, the darker it gets, the sort of longer you've been disengaged. So basically we laid down these intervals because people should be in care. They should be making a visit to care about every 6 months. So if you go 6 months without any sort of encounter with the care program, we count you as disengaged. So here's another example of a person who, here's day 0 when they enrolled, they were off treatment for 3 visits. They were engaged in care, but then they were lost to care. And this vertical line is, in a sense, the maximum amount of time we might have for that person. So this is a person who, because of staggered entry into the care program, might have had shorter potential follow-up for that person. And so what we get in the data set we use, we get about 100,000 copies of individual, I would call them almost individual data sets that look like this, where it's, visit process, a CD4 and other time-varying covariate process, and then information about being on treatment or off treatment. Now, what this plot shows is that, so we're gonna actually use this cohort to make causal and predictive inferences about different things in the HIV care cascade. I wouldn't like overinterpret this plot here, but what it means is that this is like the data that are available to us. So if we want to make inferences about things sort of going forward in time, when we line up the data, if we think about 0 as a time of enrollment, people that were enrolled a long time ago, we have more data on them. People who just enrolled, we have less data. And so this sort of observation pattern where you have just, less and less data as you project forward in time, that's kind of a typical pattern. And the reason I'm bringing this up is because we're gonna eventually make some causal inferences, make some causal projections. And what you'll see is that one really important part of this is uncertainty quantification. The further out we make our projection, the more uncertainty we have about our inferences. So what I'm going to do is just kind of walk through things you can do with the data and then show where machine learning can be implemented. for predictive inference, and then show why machine learning these days is so important to drawing causal inferences.
Joe, there's a couple questions. Do you want to take them now or do you want to wait?
Oh yeah, sure. I can take them now.
Okay, so the first question is, can both causal and predictive inference involve an intervention and an outcome measure? And if so, could there be both a predictive and causal relationship between an exposure and an outcome?
Well, I guess, I mean, there's a lot in that question. I guess for the purpose of this talk, I would say that the short answer is yes, but the long answer is that the two components would have to be separated out. So if you're asking a question like, can I predict what would happen if I intervene in a certain way? That's a causal question, because you're asking essentially, what would happen if I put an intervention in place versus what would happen if I didn't? So when people sort of mix the language, they say, can I predict what would happen if I did this? Whenever we use the word if, to me, that translates it to a causal question, because you're comparing if I did A versus if I did B. So, that's what characterizes a causal question. To me, a predictive question is list the characteristics of an individual, and from those characteristics, I'm going to predict something that might happen in the future or predict what a health condition might be. So for example, feed in as predictors all the features of a tumor image. And what I'm going to do is predict whether that tumor is benign or malignant. So that's a pure prediction question. It's not asking what happens if I intervene and do something to the tumor. It's just saying, give me the characteristics of the tumor that are observed, and I'm going to try and make my best prediction about what kind of tumor it is. That's a purely predictive question. So I hope that sorts it out a little bit. What we're going to see is that predictive models are used in the service of causal inference. That's going to be sort of what I'm hoping to illustrate.
And then there's a second question. Do you deal with repeated measures of exposures and outcomes for both predictive and causal inference in this different or similar ways?
I would say very different. So again, just going back to the example I used about, predicting like tumor status. Let's suppose that, I took multiple images of the same tumor, say from different angles. That's in a sense of repeated measures. I'm just going to string those together and try to make a prediction. Similarly, if I'm looking at a trend in a biomarker, I might just say, okay, what is this? We try to use, say, like prostate specific antigen to predict whether somebody has prostate cancer. And oftentimes those predictions are based on, what's the rate of increase or decline, what's the level of the biomarker. Those are repeated measures. Those are essentially fed into, a model where those are the inputs. You might extract certain features about the trajectory, and the output is a prediction of whether that person has prostate cancer. If we're going to deal with a causal inference with time varying predictors, we're typically in a setting where the intervention could change over time. Again, causal inferences are almost always concerned with interventions. So what we saw in the previous slide is that treatment could change, like person's on treatment, then they're off treatment, then they're back on it. And we can frame lots of different causal questions related to an intervention that varies with time. A very simple causal question could be, if I put a person on treatment, is that going to be better for them than if I don't put them on treatment? And I can, in a sense, average over all the on and off versions of the treatment. A more complex kind of causal question to ask is, if I'm going to sequence a treatment where I'm going to give a person treatment for a little while, then in the example of like a dangerous treatment such as chemotherapy, for example, like give them a treatment vacation and then reinitiate the treatment, I might want to know questions like, what's the best dynamic algorithm to follow? Like, should I treat them for a month and a month off, then a month on? Should I treat for 2 months, 2 weeks off, then 3 months on? So in that case, those sorts of causal questions are very hard to extract from or to answer from observational data, because you don't have a lot of control over what the different sequences are. And in settings where you want to determine like an optimal sequence, then it's usually best to sort of think of some sequences in advance and design a study, or look at an observational data set where there's not, say, thousands and thousands of different kinds of sequences. So that later kind of sequential looking at sequential treatments, that's really hard to answer, but the causal question would be looking at which sequence causes the best outcome. That would be the causal question. So hopefully that addresses that question.
Okay, that's all we've got for right now.
Okay. Okay. So this is a summary. Let me see if I have a summary in a picture. Yeah. So this is a summary of of one-step transitions aggregated across the entire history of data that I showed you. It's about 8 years of data from AMPATH. And so what this says is that, like, for a patient that enrolls in AMPATH, if I average over time, then if they're engaged at one visit, the probability of returning and remaining engaged is about 85% at any given visit. Then engagement to disengagement, the probability of like disengaging from treatment is about 13%. If I'm disengaged, the probability of coming back is about 6%. So you can see that part of the problem is like much higher percentage of dropping out than dropping back in. And in fact, if I'm disengaged, the probability of remaining disengaged is about 94%. So what we're going to be concerned with is the following. We're going to ask this kind of a question. There are two ways of, in the world of HIV, especially in places like sub-Saharan Africa, an important question that was being asked about 5 years ago was, is it better to just treat people upon diagnosis as opposed to waiting until symptoms develop or until people like cross some threshold, some biomarker threshold? So that's like, thinking about two different policies, two different interventions. One intervention is I treat everybody immediately. The other intervention is I have a tailored treatment approach where I wait until they start showing signs of illness. And there's reasons for doing both. At least early on, it was thought that, well, if we wait a while, we'll prevent people from having terrible side effects from the treatment. But as treatments got better and there are fewer side effects, that became less of a concern. And in places like sub-Saharan Africa, the concern was really more the treatment's too expensive, so let's conserve this resource. That actually became like not a very viable argument as time went on and treatment became more widely available. So we're going to ask the following causal question. We're going to say in a care program where we had treat immediately as the policy, would that promote more engagement in care and retention in care than if we had a policy where we waited till people got sick to initiate treatment? That's a causal question. To answer that question, we're going to need to build sort of a model of the progression through care. Those are going to be predictive models. So for example, we're going to have to build a model that predicts from one step to the next, what's the probability of remaining engaged in care? So we're going to sort of build a series of predictive models that tell us how people progress through care. Once we have those predicted models fitted to data, we're going to use them to answer a causal question, which is, what if everybody got treated immediately versus what if everybody what if there was a policy where for every individual we waited until they were sick to initiate treatment? So this is where I'm going to put some math in there, but let me just say this. This is where the math sort of lines up with just the sort of more simple numbers. So to organize these data, to sort of think about the stepwise progression through care, I can make a tabulation of the stepwise progression. So here's like at any given time, here's the previous state. They were either engaged, disengaged, transfer, or die. And then at the next state, they were either engaged, disengaged, transfer out, or die. So the ones I'm focused on are these four right here. So this is an overall average, right? Overall, the average probability of being engaged in care is 85%, but that probability isn't the same for everybody. The probability of remaining engaged in care differs from one person to the next. Likewise, the probability of being disengaged varies from one person to the next. Not only that, it varies over time. So this is just, as I said, averages over the entire time period. So what we can do, I want you to just focus on the middle of this slide. This is a probability. We can model a probability of transitioning from state K to state L, like from disengaged to engaged at a particular time J, which is like indexing time since enrollment. And this is sort of like, the input output. We can input individual characteristics of a person and any time varying covariates, let's call them X. We plug them in, and what the goal is to return some prediction about whether they would remain, engaged, disengaged, etc. So for example, here are some of the predictors we might use to predict like what happens from one time to the next. We might use CD4 count, their baseline viral load when they were first enrolled in care, height and weight, all kinds of stuff. And some of the things that might really impact remaining engaged, like treatment time to clinic, enrollment year and calendar year. These are like, period and cohort effects that also could be important. For example, calendar year is important because remaining engaged in care, the probability was lower very early on in the epidemic, but better as time went on. So there's a lot of numbers on this table, but this is essentially a regression model, and let me walk you through it. You might remember, like if you've taken a regression class, that in order to predict a variable that has multiple levels, like disengage, transfer out, or death, you use what's called a multinomial regression. It's kind of like a logistic regression, but for lots of categories. So let's suppose we're just looking at, now this is important to think about, like let's look at one model at one time. So we're looking at the probability of remaining engaged in care. The probability of, if I start out with being engaged in care, what's the probability that at the next visit, I'll be disengaged or transfer out or die? So it's transition from engaged to disengage, transfer, death, but only at one time point. And there's lots of time points. This is just one of many models that we could be fitting. But if we just look at this one time point, what we see is that there's no effect of the covariate value will be 0. The covariate value for age is negative, which means that the older you are, this is like a double negative, but the older you are, the less likely you are to be disengaged because that coefficient is negative. If you're male, you're more likely to be disengaged. If you have advanced disease stage, if your WHO stage is higher, you're more likely to be disengaged. If you're married, less likely to be disengaged, and so forth. So what we see here is that this is kind of the typical regression setup, that you can fit a regression model, and I've fit the regression model so that, age is linear, enrollment year is linear, travel time is linear, etc. I've kind of made a lot of choices when I fit this model. I've also decided that there's no interactions, and in that case, like I'm making kind of a simple model. It's not clear like if that model is correctly specified. So as a predictive model, this is why machine learning as a predictive model may or may not be a great model, and this is where machine learning can help us out a lot. So okay, so let me skip ahead a little bit and say, like, I want you to hold that regression model in your mind and say, like, okay, I'm going to need that regression model soon to make causal inferences. So just to remind you of the causal question we're going to be answering, we want to answer the question of how would the treat immediately policy, that is, treat people as soon as they arrive in care with a positive HIV diagnosis, how does that impact progression through the care cascade? So basically, this is a causal question. Policy 1 is I'm going to treat immediately upon enrollment. Policy 2, which is sort of like the policy that was in place before, is I'm going to treat when a CD4 count falls below 350, basically when a person becomes sort of symptomatic in terms of their biomarker. And the outcome I'm going to look at is state membership probability. So to make it very, very focused, what I'd like to do is ask the question, will engagement and retention in care be higher or lower if I have a policy in place that says treat immediately upon enrollment? So let me take a little bit of a detour and talk about like how we think about a causal model in terms of pictures. All right, so this is a simple causal model. So this is our intervention A. The intervention can impact, we're ultimately interested in some outcome like retention and care. I'm going to call that S, and I'll put labels on these in a minute. So I ultimately want to know if I intervene using policy A, is it going to affect outcome S, but it affects S through some intermediate variables. So A might have an impact on like, CD4 count. Treatment might increase CD4 count, people feel healthier, they're more likely to show up. And the intervention in some cases might actually even have a direct impact. Like if you put someone on treatment, just the act of putting them on treatment might make them more likely to come back because they have to come back to the clinic to pick up their antiviral therapy. And then there might be some other unmeasured variables here. I'm largely going to ignore those for now, but there's also unmeasured variables that could impact both this intermediate outcome and the outcome I'm interested in. So the big picture is that we're interested in the overall effect of A on S. It could be a combination of its direct effect on S and its effect on S through some intermediate factors. And the intermediate factors could be complicated. I'm just going to be looking at CD4 count as a variable, but there's lots of intermediate variables that could be affecting the outcome. But here's the big point, and this is the connection from causal to predictive inference. So this is a picture of a causal model. Each arrow represents a causal effect. So this arrow is the effect of A on X, the effect of X on S, and so forth. So if I want to draw causal inferences, I have to actually have models that correspond to some of these arrows. So in particular, if I want to draw a causal inference about this model, I need an observed data model that tells me how X is predicted from A and how S is predicted from A and X. All right, so these are predictive models. My input here is A, it tells me how X is impacted. This is a predictive model. If I plug in A and X, it tells me how S is impacted. So it's not the causal effect of A, it's a predictive model in this case. So I'm just going to walk you through an algorithm that's used for causal inference. It's not the only way you can do this, but this is an algorithm that's used pretty commonly. It's called the G formula for people who sort of pay attention to these terminologies. So let's suppose I want to draw inference about this causal process, and I know a model, or I can get a model from data that tells me how to predict X from A. That's basically this arrow. And another one that tells me how to predict S from A and X. So basically, it's the second one tells me how A impacts S and how X impacts S. All right, so it's basically telling me how these two arrows feed into S. And if I had those models in my hand, all right, if you told me those models, then what I could do is, this is how causal inference works. And this is sort of like, it seems simple to people, but there's lots of assumptions that go into this that you can't test with data. But, the basic idea is this. If I'm interested in comparing, say, intervention number 1 to intervention 0, what I do is I take these predictive models, all right, and I plug in the intervention value that I'm interested in. So I plug in, if I'm interested in treat immediately, I plug in intervention value 1 here and here. And then I sort of simulate the outcome sequentially. I simulate X for intervention 1. And then once I have that X that's predicted, I plug it in and I can generate a prediction of S. So I start with like the intervention, fixing the intervention, and I sort of simulate forward. And when I'm done simulating or generating predicted values, I compare the simulated values of S when I fix A to be 0 and when I fix A to be 1. All right, so I'm going to tie this together now and show you where machine learning comes in. So basically this connects predictive and causal inference. I know it's one talk in just a few minutes, but the essence of this is if I have predictive models that tell me how these observed values are related, the way I draw causal inference, again, after invoking some assumptions, is that I essentially take my predictive models, but I fix the intervention to be either one value or the other. And after fixing that value, I generate predictions and then average them. I average the predictions I get under A equals 0 and the predictions I get under A equals 1. Essential to this is that I have these models and they're good predictive models. So notice my causal inferences are depending on my ability to generate accurate predictions. If I can't generate accurate predictions, my causal inferences are going to be biased. Now, if you remember, there's longitudinal data here. So we have like many, many time points. So I have to basically fit predictive models for a longitudinal version of the graph I just showed you, which means I need a large collection of predictive models that predict, for a time J, the state at J, given all the information available in the past. Basically, those are my inputs. And X, which is CD4 count, conditional on all my information leading up to that. And here's where machine learning comes in. I showed you before like a multinomial regression fitting one model at one time point. But now I need lots of models. I need basically 2 models at every time point. It's really hard to say, like, is my multinomial regression correctly specified? Like, should age have been linear or should it have been nonlinear? Should there be an interaction between some of these? These are things that are sort of almost unknowable empirically. And so this is where machine learning, if you have a good machine learning algorithm, you can in a sense like let the machine learning algorithm figure it out. So this is where I think of like, I'm saying almost nothing about the technicalities of machine learning. Essentially what we do is in our particular application, we use machine learning to fit these, we have like 12 different models, 12 different time points, 2 models at each time point. That's 24 different models. Each model has 30, 40, 50 covariates, depending how far along we are in time. And so we train these models on 50,000 individuals, the data record for 50,000 individuals. And then just to make sure that these models are sort of returning good predictions, we validate them on another 25,000. So it's like, this is the sort of the training set and the test set. And then once we've trained the data, we tested the models, make sure they generate good predictions. Then what we do is we actually take another 10,000 subjects and we generate actual predictions to get our causal inferences. And I'll just say, the predictive models that we fit at all these time points are called Bayesian additive regression trees. I would sort of be, although I like these models a lot, I'm sort of agnostic about which models are used to generate the predictions. It could be anything, but it should be a good model that generates accurate predictions without overfitting. You can find that out in the testing and training component, and Bayesian additive regression trees tend to do a nice job in this case. So this is just a picture where I'm showing you, these are features of the distributions that or the models we're trying to look at. So after we fit the models using Bayesian additive regression trees, what we do is we then compare the predictions against the observed data. So the prediction that, for example, this is one, most of them you can't really see the predictive confidence bands, but what we've done is the red line is sort of the prediction and the blue dots are the observed data. And in order to move forward, in other words, like you fit a model, this is in a sense of validation of the model. It says I can use the predictive components of my causal model to then generate what I think are going to be accurate simulations of the causal effect. Right, so these are once we fit this series of models, so what we've done is these are our like causal simulations. So we fix, the intervention to be treat when CD4 is less than 350. And then next we're going to do is fix the intervention to say treat immediately. So what we see here is that, I guess, let me see if I have to move this window to get the colors. Okay, so the turquoise here, we're looking at transition from engagement, and the turquoise is like basically the probability of going from engagement to engagement. It's probably being retained in care. And what we see is that under this policy of treat when CD4 is less than 350, retention in care has the biggest dip in the first period of treatment. That is like right after people enroll. But then after those who sort of survive this big dip retention is actually pretty good. So what we're trying to avoid is this big dip in retention and care. And if we simulate under the alternative scenario where we treat immediately, you'll see that the dip is attenuated. So again, the x-axis is time, the y-axis is probability of retention and care once you've been enrolled. So here's old policy and new policy. So we're basically taking our whole family of predictive models. For this one, we're plugging in A equals 0, the old policy. For this one, we're plugging in A equals 1. And those are our simulations. So we see that there's some evidence of a positive causal impact of treat immediately. We can also look at it as like average state membership probability. And I'm sorry for switching colors, but black is engaged in care. Red is disengaged, blue is mortality. X-axis is time since baseline. This is like, so if I were to enroll a cohort, this would be time 0 of enrolling that cohort in care. And then the y-axis is probability. The probability is up to 100 because these bins each contain 100% of the patients that were enrolled. So obviously at time 0, everybody's engaged. And you see it's really these first two periods where the disengagement risk is the highest. So this is the scenario under, now we've got to move this window again. Let's see. This is a scenario under the old treatment. And then if I generate simulations for under the new treatment, it looks like this. So this is the old treatment. This is the new treatment. And again, what I've done is I have a whole family of predictive models that generate predictions of this system. I plug in A equals 0, I get these predictions. I plug in A equals 1, I get these predictions. That's the causal effect. So finally, what I'll say is that it's important to be able to do inference. And you'll notice that if I look at this, oops, this versus this, there's no uncertainty. I'm just showing you these predictions and they all sort of look equally accurate. One thing that Bayesian additive regression trees does do that's nice is it gives you a sort of a variance or predictive uncertainty after applying the machine learning algorithm. So here's time since enrollment for a cohort. And what these confidence intervals are showing us is the difference in percent engaged for the old policy versus the new policy. And positive difference means higher probability of engagement under the new policy. And what's nice about this is that, well, first we see that treating immediately, tends to be causing people to stay in care. The confidence intervals are narrow early on, but also reflect that as you have less and less data, essentially as you're leveraging the model a lot more than the data at the end, the confidence intervals are much, much wider. So the nice thing about these Bayesian additive regression trees is you can recover this uncertainty. So you might wonder, like, what is it about this? So the theory, when we talked to the behavioral scientists and the clinicians on the ground, it was really like, it was two things. The things that were causing people to drop out were people thinking they didn't need their treatment. That is, especially when they didn't get treated early on. If you send someone who's been diagnosed with HIV away without treatment, they probably think, oh, I'm fine, because the symptoms actually don't show up often right away. There's a long lag time between infection and showing symptoms. So giving someone a treatment right away, not only is it better for their health because you sort of get ahead of the infection, but it gives them a reason to come back, and it sort of focuses their mind on the fact that I need to be coming back for this treatment, like this is necessary for my healthy survival. So I would say that, here we've done a causal inference looking at evaluating different treatment policies. All causal inferences are for observational data without randomization, are extrapolations from observed data fitted models, typically predictive models. And we had a really complicated set of predictions we had to string together so that we could look at like causal extrapolations under predictive models. And so that's where the machine learning comes in, is to enable us to fit those models and have some confidence that they that they have decent predictive accuracy. And I hope, and I don't, it's hard to do this in an hour, but I hope that at least to some degree, the audience has been able to appreciate the difference between a predictive inference and a causal inference. So a causal inference is an answer to the question of what will happen if. Like, what will happen if I intervene in one way versus if I intervene in another way. Predictive inference is if you tell me the state of affairs right now, if you input a person's characteristics, just give me a prediction about what happens next. So when we did the predictive models, one of the characteristics we're putting in is the person on treatment? So this would give us a predictive model of, those who are on treatment, those who are off treatment. To do the causal inference, what I did was I took those predictive models and I switched treatment on for everybody, generated predictions. Then I switched treatment off for everybody, generated predictions once the models were fitted. And sometimes, like, without going to excruciating detail, it might be hard to see the difference, but that's how the predictive models are used in service of the causal models. So I just wanted to give like a quick shout out to the group of statisticians and data analysts. This is part of a much larger collaboration that involves training and capacity building at Moi University in Kenya. This is a advanced methods conference that we held. I think, this is way pre-pandemic. I think this is 2018 or possibly 2017. And these are some of my collaborators. So at Brown, Yi-Jin Xu is actually at Johns Hopkins now, but Rami Kantor is a longtime collaborator, as is Tao Liu and Allison DeLong, and Hannah Lee contributed to a lot of this work. She's at the FDA. And several collaborators from around the AMPATH consortium also contributed. And I guess I should acknowledge too that this work has been funded by a number of different sources, including the NIH, the USAID, and the Center for AIDS Research here at Brown. And then finally, there's a bunch of references here. I'd be happy to share them if somebody wants to email me. My email's in the bottom left here. So I'll stop there and just answer any questions that there might be, and just say thanks again to Chris and the CTR group for extending the invitation. I really appreciate it.
Thanks, Joe. That was an amazing talk. I've got one question in the chat, which I'll get to first, and then if anyone else has questions, either put them in the chat or raise hand, and I guess I can call on you. So the question in the chat is, does the multinomial regression analysis in the example take the repeated measures into account?
Yes. So the way it does that is we actually fit a different multinomial regression at every time point. We have enough data to do that. So often if you're looking at longitudinal data, you might fit a multinomial regression where you combine all the data and sort of model the time trajectory somehow. But, just to go back to that fitted model, this was, so this model here was just a model for time point 3. So we had enough data to fit a separate multinomial regression at every time point. What we did do is we made this is again getting into the weeds a little bit. We made what's called a first order Markov assumption, meaning that the transitions from, say, time 2 to time 3 could be predicted solely from information available at time 2. We could elaborate the model and make it even more complicated, let it depend on information available before that, but these models seem to fit pretty well, so we didn't extend that assumption.
All right, I don't see any questions. Joe, I just had one. If you could say something about how you might handle missing data in these problems.
So the state variable wasn't missing for anybody. So that's kind of, when one of the states is that you've dropped out of care, that solves that problem. But we were missing CD4 count. I wouldn't say we're missing it necessarily as much as it wasn't measured at every time point. So if you look at the bottom here, we sort of parameterized the CD4 part of the prediction with one indicator of whether the CD4 had been updated in the previous interval, and then if so, this is this last covariate is the actual value of the CD4 in the log scale. So when it comes to predictive models, like some people recommend imputing the missing information that's used as the inputs. That you can do that. But ultimately, even if you're predicting information that's going to be used for the inputs, you're typically using information you already have to do that. So for a lot of these models, if the goal is just prediction, I'm not trying to draw inference about the effect of CD4, I'll code incomplete covariates like this, a missing data indicator, and then the value of the covariate if it's observed.
Okay, let's see if there are any other questions. I don't, oh, there's one. Okay. What do you think how would you handle measurement error in a machine learning sense?
What is the thing they say very carefully? This is a really good question, and something that, you know, maybe this is a like sort of a next frontier of research, because or so, you know, I don't know if it's a frontier. There's a lot of work on measurement error in the statistics literature. I don't know how much there is in the ML literature. There could be a lot, but you know, covariates measured with error are really important. And I guess you know, there's two ways to think about it. One is you have to ask yourself, am I interested? Let's suppose it's CD4. So CD4 has measurement error because it's an assay and you might be not getting the actual CD4 count. For things like that, if you're trying to predict an outcome where the decision is made based on an observed CD4 count, I don't know that the measurement error is all that important, because you're writing down into your predictive model the information that's used to make the decision. But the real danger with measurement error is like misclassification. So if you have some binary or categorical covariates in a model and these are misclassified, that's an obvious source of predictive bias. So, you know, I think that sometimes the best we can do is say, if we think there is some sort of misclassification, if it's a variable that really matters, investing time to get you know, like a validation study or something along those lines would be really essential. So you know, in this particular example, I don't address measurement error at all. That's not to say it's not important. It's really important. And it's good that this is being raised. So like I said, there's a lot of literature a lot of work in the stats literature dealing with measurement error for regression. I think it's beginning to make its way into the ML literature that I've read, but we're still a long way from home, and there's probably a lot of issues there.
Okay, I don't see any other questions, and we're at time. So let's thank Joe for a great talk. And I believe this is the last talk in the series. So you know, stay tuned to the Advanced CTR website for upcoming talks.
All right. Thanks again,
Joe.
everybody.
All right.